So what we're going to work on here is work and power equations, basically. A few definitions, a few examples of doing work and not doing work. Well, to start off, if I were to define work, what we have in the PowerPoint here is just that it's a force exerted over a certain distance. And that's not necessarily the one I want you to put down, because I'm assuming, if you're watching this, that you've also done the energy skate park. That energy skate park, and what we'll talk about later when we do energy notes, is that doing work gives or changes the energy in a system. Okay, whether that be kinetic energy or potential energy or chemical energy, whatever kind of energies we're interested in. But really, work is force exerted over distance. It's just really describing the mathematical equation of it, not really giving an example of what it is. But it's the amount of energy given to a system. Okay. But if we look at just the math is pretty simple. Work is force times displacement. Examples of doing work would be to actually lift something over your head, like take a book and raise it above your head. What you're doing there is you're applying a force to that book by holding it and lifting it. It is displaced from its original position by that force. So you are doing work. Walking up the stairs to my classroom. In order to do that, your legs lift your body up one flight of stairs, therefore it's done work. Things like pushing a desk across the floor requires a force to move it that distance. So that would also be an example of work. Examples of no work being done. Holding a book, but not moving it. Normally I start this conversation off with those warm-up questions by having a student hold a book or two with their outstretched arms until we finish those pre-lab questions or warm-up questions. And they get really tired and the arms are shaky and they feel tired at the end. And I ask if they have done work. And most people agree that he has, because he has, sore arms, exerted a lot of energy, that kind of thing. But in the mathematical sense, since that force he was using did not cause the books to displace, he did not do any work. Likewise, when we did inertia ball, a ball rolling across the floor. Now, you may have done a little work to get the ball rolling, but since the motion of that ball no longer requires a force, the force is zero, so therefore no work has actually been done. If you've ever done a wall sit before, all right, those are really enjoyable, I'm sure. Your legs are trembling and afterwards, and you can barely stand up. And you may feel exhausted, but since the wall doesn't move, you did not do any work. You didn't add any energy to the system when we start talking about work as adding energy. So let's talk about the work units. Again, first off, I almost forgot. Work is force times displacement. You need some other equations to rework that. We could also rearrange that to find the force by taking work divided by displacement, or displacement is equal to, all right. But if we look at this, the units that we normally use for force are newtons. The units that we use for displacement, meters. All right. So what we get is that this idea of Newton meters. And just like a Newton is really a bunch of other units, kilogram meter per second squared, wrapped up into one unit, a joule, all right, is the same thing. It's just the combination of Newton meters. All right. Let's look at power. Power is the rate at which work is done. It's how quickly. Notice how before work didn't really require any time units. In this case, how quickly you can do that work is. So power equals work divided by time. So you could also rearrange that for work equals power times time. Or you can solve for the time as work divided by power. If we look at the units, again, you got joules for the work. Time is seconds, so joules per second. And just like in 4 with the joule, we wrap up at joule per second in another unit called a watt, which may sound familiar, like light bulbs measured in watts. A 60-watt light bulb, a 100-watt light bulb. All right, that is measuring the amount of power it is using. So a few practice problems. If we want to calculate things like how much work is done to lift a 10 Newton weight 5 meters in the air in 4 seconds. First off, this time is irrelevant. Work is not dependent on how quickly you do the work. So only thing we need is the force applied to lift and the displacement that it's caused. So work is force times displacement. 10 times 5 is 50 joules. If I want to know the amount of power that was used, well, now we take that amount of work, we take the amount of time it took to do that work, plug it into the power equation, work divided by time, and you get something like 12.5 watts of power. Another one. How high would a 10 kilogram mass need to be lifted so that a student does 500 joules of work? Yeah, unfortunately, we don't have force, okay? We only have the mass and the work. So how can we solve for the displacement if I don't have a force? Well, if you think about it, holding a book that, all right, stationary in my hands would have a force diagram like this. I could solve for this push, this force that is causing it to be lifted, all right, if I'm holding it steady, all right, or if I'm raising it up at a constant velocity, same force diagrams. This force of gravity is just 10 newtons per kilogram times 10 kilograms. Remember this equation, Fg equals mg. So that means that weight is 100 newtons and the force required to lift it is also 100 newtons. Which is why you can then come up with that force of 100 newtons and then plug it in and solve. And you get an answer of 5 meters. One more. How much time would it take for a student to lift a 10 kilogram mass from the previous question so that he uses 1,000 watts of power? So we know the work from the previous question. We know the power. Time is work divided by power. And voila, 0.5 seconds.